Good morning or good afternoon, wherever you may be around the globe. This is One Moose, Two Moose, Three Fields More. I'm Joseph Alexander Brown. I'm an associate professor and head of lab at Annapolis University. This presentation is in regards to a game theory model of a biological system and how we're using this as part of being a teaching tool, and hopefully it's going to become a competition going forward at CIBCB. So to begin with, we have our team that we're working with, which is split between the University of Guelph in Canada, Annapolis University in Russia, and Brock University inside of Canada. And these are all various places where we have moose. So it kind of lines up with that. My goal in kind of coming up with this sort of model is having to do with my kind of other hat at Annapolis University. I'm a teacher's trainer there, and I work with trying to create new models of engagement with students from the perspective of active learning. And the idea of active learning is that learning is not just based upon lectures and readings, but that we should really take all spaces inside of the university to act as learning environments. So professors and TAs at Annapolis are encouraged to really to step from behind the podium and engage with students in a more hands-on approach and create learning styles that work towards this more kind of engaging students with the materials. This can also include non-classroom events. So we have a group that gathers for Pi Day, we have hackathons, and we also have game jams to have students engage with the materials. One of the classes that I was having real difficulty with engaging students with is inside of game theory, and game theory being one of these highly mathematical areas to some people seems, rather boring. Oh no, we're going to have to do some more math. And also people have this ill-begotten, in my mind, idea that math is scary. But really math is a way of kind of understanding the universe and understanding what is happening inside of our world. And it does have kind of physical ramifications. So in this case, for example, we were taking a look at basically decision-making using game theory. And here you can see two students in the pre-COVID age firing at each other with Nerf guns inside of my classroom, simulating a duel inside of this class on mathematical game theory. And then we looked into what was kind of the mathematics behind their decision-making process. So anything that we can kind of do to engage students with the materials is a rather good thing in our mind in order to kind of reduce the amount of fear that's inside of the mathematics and to make it a bit more fun. And if you're having some fun, then hopefully also it's helping you to want to engage with the materials more and increase your learning experience. As we have these two universities there inside of Canada and inside of Russia, we can take a look at the ranges of moose over this, and we can see that it pretty much blankets both of these countries have a moose population. So it is kind of a cultural touchstone for the both of us. And the moose here across this area, well, during rut, they like to fight with one another. So they're known to be an aggressive and territorial animal. Here, for example, is an image from National Geographic in which they are fighting in the middle of a downtown street inside of, I believe, somewhere in Alaska that this fight happened. And they have evolutionary adaptations to allow for such fights. They have huge antlers that come in over the summer, and they shed them over the winter months. So over the breeding season, they will have these in order to have these types of fights. And for anyone familiar with kind of the up north regions inside of Canada or inside of Russia, we've seen these types of things happen. And usually there's some rather interesting videos that come out now and again. I guess the only analog I could maybe see inside of Australia might happen with kangaroo populations if they're anything to do with the ones that I see inside of Looney Tunes. They like to box with each other. But this is basically their type of behavior inside of this season, where they will fight for territorial gain inside of it. for breeding rights, and for food and forage rights over various territories. This we saw as a great way to kind of glue it into then a game theoretic model. So we have some fields that have some resources of food, and they're going to grow via a sigmoid function. You can get some more of the details inside of the paper, but the idea generally is that early on the field grows rather slowly, and then it grows rather fast for a while, and then it reaches kind of a cap out point across it, which is pretty close to a lot of different foliage. And the moose can select which field it wishes to move to in a turn. There's 3 different fields that we have. If there's another moose there, well, they fight. They get no food, and the field is damaged. And this is something that you can kind of see after these fights, is that they will actually damage trees in various areas around it when you walk inside of these regions. If they're alone, however, they eat. The field is reduced in terms of its growth, but they have that gain inside of it. A field that doesn't have any moose on it just grows. The winner over this model is the moose that eats the most over the 100 rounds of the game. And so this game was given to the students as a competition. Students would put in various models of their own making, and then we would compete these moose models and see which one is the best type of moose. So putting into our idea of the active learning model. So we can see here, if 2 moose select the same field, the field loses a point, the moose fight and get nothing, and the other 2 fields are able to just grow. If they select different fields, then they eat some amount. Each moose gains a certain amount of score, and the other field is left to grow. So we can see that this is really a very, very simple biological model, but it has an interesting dynamic due to its requirements of discoordination. So moose have an incentive to kind of not fight with each other because they're not going to eat and score, and they'll damage the landscape around them. They're going to prefer not to bump into each other. However, there's also an incentive to go to the fields with the most growth, that have the most food on them, in order to maximize their score. So there's kind of a pressure to move the 2 moose to the same field if it scores very high. The first 2 tournaments were conducted in the 3rd year class of game theory at Annapolis University. Agents in this case were programmed in Java, as is the testing software. So if you're interested in putting in an agent, we have built a testing bed inside of Java for that, mostly just having to do with the fact that that is what our students were practicing in other classes as in their software development. We wanted to make it more about creating a cool model rather than programming. Good agents were found. We did an analysis over the student submissions over these 2 years, and we ranked them, which provided us with some interesting findings about the problem. In fact, the top 8 agents submitted by students showed almost the same strategy. Created agents that had this handshaking properly, in which they found a field that they could kind of rest in. So we had 3 fields, so 2 of them kind of became resting fields where the moose would just sit and kind of, just eat the small amount that's there, and then wait until it saw the 3rd field grow to a point where it was viable for competition. And then they would proceed to combat over that. We can kind of see this almost as a home territory, which provides a small benefit each round as the moose is still eating the current location. And then there's an attempt to capture that 3rd field when the resources make it worth a fight. So this is very close to some of the old iterated prisoner's dilemma contests that happened. There was early ones by Axelrod in 1981 and 1984 that examines the use of tournaments inside of this. They created lots of different agent types, and there was lots of further contests inside of IPD. But given the fact that it's been around for, since the 80s, I think we've kind of reached a point where we might want to try and look at a different problem. In terms of the evolutionary results, we then also set about examining this game via our own evolutionary process. And we found that the coevolution has a property of density-dependent selection. So in this case, what happens is a strategy is inverse proportionally good dependent upon how many of them exist inside of the population. That is, if I have too many clones of my strategy, I actually do poorer than if I was a strategy all on my lonesome, which in some ways is very different than what we see in the dynamics of Iterated Prisoner's Dilemma, where we have this idea of an evolutionarily stable strategy, one where it takes over the entire population. One of the things that the IEEE is looking into is encouraging more contests at its conferences. Being a member of the BBTC committee, we're looking at how do we then create contests that will work outside of CIBCB. And therefore, the idea of this was also to create a more competitive event that could be run at CIBCB that included more computational biology. So we plan to make this type of modeling into a contest for next year. So at this point, please begin thinking about this problem, and hopefully next year, you and your students can come with a better agent than the one that we've created in order to face off in this moose battle. However, there's lots of places that we can expand to. As I mentioned, this model is relatively simple. But what about different growth rates or biomes on the various fields that are inside of it? So instead of one that always is growing at a certain set rate, there is different ones that grow at different rates, different times, and have different abilities. What about the number of moose? In this case, we only looked at 2 competing against each other, or more fields. If there's more fields, then perhaps there's more chances for other strategies to be created. There was a question that was great from one of the reviewers that had to do with what's the level of knowledge that the moose has. In this terms of game theory, usually we say that it has complete knowledge, but this is not necessarily the case. Perhaps the moose can only remember things so many stages back. How about having a movement cost between the fields? In this case, any field could be moved to at any turn, but maybe it's more of a map and moose move between fields that are connected via a graph. We can also look at health of the moose depending upon past successes. In this case, if 2 moose fight, it kind of doesn't matter who wins. Both of them end up with no resources, and both of them end up damaging the field. But what if a healthier moose, that is one that has ate more within the past so many rounds, is able to win that fight and therefore feed in that round as well? And finally, and perhaps not great for CIBCB, but going forward in general, we can have other themes on this game than moose. So thank you very much for your attention, and I do hope that you will join us next year for a competition on this. I'm Joseph Alexander Brown. My contact information is there. It's jbrown@annapolis.ru, or you can find me on my Twitter at @jb03hf. Please enjoy the rest of the conference, and I'm sorry that I didn't get to see Australia because, as you may understand, I'm also a Joey.